All right, continuing with our enzyme discussion. So, enzymes are indeed proteins. I mentioned before they can be RNA. We'll talk about that again when we get to ribosomes. But because enzymes are proteins, they are subject to the same limitations that proteins have had that we've discussed throughout this semester. That proteins are sensitive to pH and temperature because those things interfere with weak force interactions and cause proteins to misfold. Same thing is true for enzymes. For an enzyme to work, it needs to be in that native conformation. Remember that native conformation means the fold that it normally has when it does its job. If it doesn't have that conformation, it's not going to be able to do its job because the active site is not going to be the right shape, the right amino acids won't be in place, and that means that the enzyme is going to lose its activity. So we know this is called denaturation. We've learned about this already. When you deviate from that native conformation, that can lead to denaturation. And denaturation for enzymes means a loss of enzyme activity. So, like we saw with hemoglobin and myoglobin, sometimes enzymes as well require additional components that aren't included in the polypeptide chain that leads to the formation of the tertiary native structure. So we have some names for these. Cofactors is the first example. That's usually one or more inorganic ions, usually metal ions, that we use within the active site. Some examples: iron. We saw iron 2 plus in hemoglobin and myoglobin. Magnesium 2 plus, manganese 2 plus, and zinc 2 plus. Again, all these are metals and very commonly seen as cofactors in various enzymes. A coenzyme is also required to be present in the active site like cofactors, but coenzymes tend to be larger organic molecules, so more complex organic or metallo-organic molecules. And many of these can be derived from vitamins that we take in through our diet, and that gets either used directly or modified in some way to become the coenzyme. An example is heme. That is present in hemoglobin, of course, but cytochrome A3 is actually an enzyme that utilizes heme. And vitamin C, of course, or ascorbic acid, utilized by prolyl 4 hydroxylase. I left out the XY here. That is, of course, important for collagen formation. So again, it's really important for the enzyme to work. You have to have the coenzyme, or it just doesn't work well. Here you can see heme, which you've seen before, coenzyme. Some of the enzymes that utilize heme actually need iron to be in a +3 state rather than in a +2 state, and that ends up making a big difference for those activities. So this is, of course, +2 iron, which we see in hemoglobin. Okay, that's a repeat. Okay, and the third type of additional component is called a prosthetic group. And it's basically the same thing as a coenzyme or a cofactor. It's just tightly bound to the active site, in some cases covalently bound. I don't really use it, and I'm not going to test you guys on it because prosthetic group is it's kind of an outdated term, and pretty much at this point, we just refer to them as either cofactors or coenzymes, and we can just go ahead and make the distinction as to whether it's covalently bound or tightly bound. So just be aware you might see prosthetic group. If you do, it just basically means usually a coenzyme, not a cofactor, a coenzyme that's very tightly bound or even covalently bound to the active site. I'm not going to test you on it, but you might see it on the MCAT or you might see it somewhere else. So just be aware that people do use that term, but again, it's kind of getting phased out at this point. And some more terms. If you do have an enzyme that requires a cofactor or a coenzyme, if that cofactor or coenzyme is present in the enzyme, we refer to the enzyme as a holoenzyme. The way I remember it is it's whole, right? It's got everything it needs to do its job. So the holoenzyme means the enzyme plus a cofactor or a coenzyme. Apoenzyme would be the enzyme without the cofactor or the coenzyme. So you just have to memorize these terms and make sure that you know them. That brings us to enzyme classification. So we're going to have 6 different classifications that you need to be aware of, and you should be able to identify when an enzyme falls into one of these 6 classifications. And again, it's based on the reactions that they catalyze. Remember that a lot of enzymes are named by just taking whatever the substrate or activity that they do and adding ase to the end. For instance, urease hydrolyzes urea, so it's just called urease as a name. DNA polymerase generates DNA polymers, so that's where the name comes from for that one. And some, again, have names based on more of a broad function before they could have been more specific, like pepsin, which is a digestive enzyme. The Greek root is pepsis, which I believe means either, I want to say it's like acidic or something like that. I'm actually not sure. And lysozyme, named for the fact that it lyses bacterial cell walls, but this is a very generic name. You know, you could say like bacterial lysozyme or bacteriase or something. But lysozyme, again, very general name for this enzyme, and it kind of stuck. So this is the name that we use. So long story short, some enzyme names are perfect, very simple and make sense, and some of them don't make sense at all. As always, and we've seen this many times in science, in biochem, and everything. Uh, like the whole entropy enthalpy thing. Why do they both have to begin with E? It's confusing. An example of a protein name that's really ridiculous, again, as I mentioned in class, sonic hedgehog. This is a developmental gene that's really important, and the protein generated from it. Really important for limb growth, and defects in sonic hedgehog can cause developmental issues. And so that name is one of the last names before the people who make these choices, the nomenclature people at the Système International in France, they basically kind of made it so that scientists would stop using these kind of more ridiculous names like Sonic Hedgehog. And again, this is Sonic Hedgehog, a character from that game. Okay, so naming system for enzymes. Again, if you're following the standard nomenclature system, you basically want your enzyme to fall into one of these 6 classes and name it based on that, and maybe add in what the substrate is or what the product is, something like that. So again, going to need to know each of these classes, and it's based on the type of reaction that are catalyzed by these enzymes. The first one, pretty easy, oxidoreductases. These transfer electrons from one group to another. Many times, especially in our central metabolic pathways, these enzymes are going to have the name dehydrogenase. Very commonly seen, and wouldn't hurt to make a note of that, but we'll talk more about that in Biochem 2 if you come along to that class next semester. Transferases, group transfer reactions, so basically transferring a group from one substrate to the other. For instance, we have our aminotransferases that switch an amino group from one compound to another, so that would be considered a transferase. Hydrolases use water to break bonds or undergo hydrolysis reactions. Lyases add a group to a double bond or remove a group to form a double bond. So lyases basically are either using that pi bond to add a group or removing a group and re-establishing the pi bond. So we call those lyases. Isomerases are just going to rearrange whatever is in a particular product. So they might rearrange, for instance, a hydroxyl group with a carbonyl group, something like that. But basically, we're not taking anything away from the substrate or adding to it. We're just rearranging it. So those enzymes are known as isomerases because they tend to create a product that's a stereoisomer to the original product. Last but not least, ligases. Ligases form bonds by condensation reactions, so basically taking two things and making one thing. When we do that, we're going against entropy, so usually requires ATP in order to facilitate these reactions. So these ligase reactions tend to be anabolic, meaning we're building bigger things out of smaller things. When we do that, typically it requires energy because we're creating more order going against entropy. So we have to pay a tax for these type of reactions. Okay, so those are the 6 classifications that you need to worry about. Again, oxidoreductases mean transfer of electrons, also known as dehydrogenases. Transferases transfer a group from one compound to another. Hydrolases break bonds using water. Lyases either add a group to a double bond or remove a group to form a double bond. Isomerases just rearrange things within a particle. And then ligases are going to take two things and make one thing, condensation reactions. And again, these typically require ATP because these are anabolic reactions. So an example of a standard name that we would use based on classifications is for this enzyme, which you can see converts glucose to glucose 6-phosphate and does so by attaching a phosphate from ATP to the glucose. So adenosine triphosphate, or ATP, becomes adenosine diphosphate, meaning it has 3 phosphates in ATP, 2 phosphates in ADP. The phosphate that we removed from ATP got attached to glucose to form glucose 6-phosphate. So that is a group transfer reaction. We're transferring a phosphate from one compound to the next. We call that, so that's going to be a transferase. The thing that we're moving, we put in front of transferase, so it's going to be phosphotransferase. And then we basically name the 2 substrates that are going to be changed. So we're taking the phosphate from ATP, so it comes first. We put a colon, and then glucose. So the overall name, using our standard naming conventions, ATP glucose phosphotransferase. But guess what? That's not what we call it. The common name is hexokinase, named for the fact that a kinase reaction is happening, something's getting phosphorylated, hence kinase. And then hexo actually comes from the fact that glucose has 6 carbons. But of course, from this name, you don't know that we're referring to glucose. So again, the common names usually aren't that great. It'd be much better if we just used the official names like this, but we don't. We give them common names, and so it's really annoying. You'll see if you come to metabolism, you'll see that lots of different kinds of enzyme names, and they get pretty variable depending on what the name is. Okay, so that is part 2.